Okay, so now that we've defined the various types of collisions and provided an equation for each one, let's clear the screen and provide some numerical values. So let's say that the red glider represents object number 1, and maybe it has a mass of about 10 kilogram. And then our glider number 2 has a mass of, we'll say, has a mass of half as much. Maybe that one's 5 kilograms. And then prior to the collision, that glider is moving to the left at 3 meters per second. Now, here's the biggest mistake, failing to include negative signs for velocities in the negative direction. So its speed is 3 meters per second, but I'm going to say its velocity is negative 3 meters per second. And our glider number 1, just for the sake of example, we can say is going twice as fast. So it has a speed in this direction equal to positive 6 meters per second. Maybe it would be helpful to put all that into a list. So let's set it up. We've got M1, U1, M2, U2. We're going to have to solve for V1 and V2. So we have an M1 of 10 kilograms, M2, 5 kilograms, U1, positive 6 meters per second, U2, negative 3 meters per second, and then we have to find the final velocity of each after the collision. So let's try case number 1 and assume that the two of them stick together. If that's the case, there's no use saying the final velocities are V1 and V2. There's just one common final velocity, V, and the equation we want to use says M1U1 plus M2U2 is equal to the combined mass added together multiplied by the final velocity. We can rearrange that algebraically and state that the final velocity is M1U1 plus M2U2 divided by the sum of M1 plus M2. If we plug in the exact numerical values that were given, we have 10 times 6 plus 5 times negative 3, all divided by 15. That comes out to 60 minus 15 over 15, which is 45 over 15, which is 3. Now, I've left the units out of the work, but I think we agree those units would be 3 meters per second. Now, as a further investigation, we say how much energy was lost in that collision, right? How much of the kinetic energy was converted to thermal energy due to the process of hitting and sticking together? So to answer that question, we need to calculate the initial kinetic energy. This is 1/2 M1 U1 squared plus 1/2 M2 U2 squared. So I'll let you grab your calculators and work that out. If you want to hit pause, you can hit pause, grab a calculator and plug in the values, and then resume playing the video after you've made your calculation. Okay, so you should have found that the kinetic energy is 202.5 joules. And let's compare that to the final kinetic energy. So the final kinetic energy is 1/2 times their combined mass added together times the final velocity squared. So this is 1/2 times 15 times 3 squared. And again, hit pause, grab your calculator, see what you get. Okay, so hopefully you agree this comes out to 67.5 joules. So the amount of kinetic energy lost, delta K, is the initial kinetic energy minus the final kinetic energy. Or we could state this as a percentage. We say the percent lost is delta K over K initial times 100%. So this would be equal to 202.5 minus 67.5 divided by 202.5. And again, check your calculator and see if you agree that this comes out to a percent K lost of about 67%. Okay, let's try this problem again, but determine what would happen if they don't stick together. What if the two gliders that have the same amount of mass and speed initially hit and separate after the collision? So I'm going to clear some area on the screen. All right. So I can't say they have a single common velocity, so I'm going to have to figure out what's the value of v1 after the collision and what's the value of v2. Well, I'm not sure I can really effectively do that if I only have one equation that says the total initial momentum equals the total final momentum. I have values I can plug in for m1, m2, u1, u2, but I don't know either of these two quantities, and with one equation for two unknowns, we're out of luck. So I'm going to have to give you some value and make up a hypothetical and say, what if we know the final velocity of one of the two objects after the collision? So let's just make up a final value and say we're going to guess that the final velocity of object number 1 is maybe, or maybe the final velocity of object number 2 is 1 meter per second after the collision. So what's the final velocity of object number 2? Actually, let me change that. I changed my mind. Let's say the final velocity of object number 1 after the collision is 1 meter per second. So it was originally going 6 meters per second. The two blocks collide, or the two gliders collide, and then object number 1 continues to plow forward at 1 meter per second. Object number 2 was going -3 meters per second, so what's its motion after the collision? All right, so the problem's been set up. The equation is m1 u1 plus m2 u2 equals m1 v1 plus m2 v2. So we're trying to solve for v2. So we have m1 u1 plus m2 u2 minus m1 v1, all divided by m2, calculates the final velocity of object number 2. If we plug in the numbers, we get 10 times 6 plus 5 times -3 minus 10 times 1, all divided by 5. Grab your calculators, hit pause, and resume playing after you've figured out the final answer. Okay, so hopefully your calculator agrees with the answer I have. 7 meters per second is the final velocity of object number 2. And once again, it's worth investigating how much kinetic energy was converted into thermal energy in this process. Well, the initial kinetic energy we already found out is 202.5 joules. That hasn't changed. This time, the final kinetic energy is not the same value it was when they stuck together. So you calculate final kinetic energy again the same way. 1/2 m1 v1 squared plus 1/2 m2 v2 squared. The only difference this time is v1 and v2 are not a single common value because they're not stuck together. Grab your calculators, see what value you get, and resume the video after you have your result. Okay, right, that comes out to a final kinetic energy of 127.5 joules. And if you take the time to calculate the percent kinetic energy lost, right, find the amount of kinetic energy lost and then change it into a percent kinetic energy lost. And I think you would agree that the overall percent kinetic energy lost this time is 37%. So what we want to do lastly is see what happens if the collision is elastic and verify that the kinetic energy lost really is 0% in the case of the elastic collision. So we've got case 1. where they hit and stick together, the perfectly inelastic. We just did case 2, where they hit and they do not stick together, but still convert some energy into wasted thermal energy. So here's our final attempt. What happens when the two of them hit, bounce apart from each other, and conserve kinetic energy along with momentum? M1U1 plus M2U2 has to equal M1V1 plus M2V2. So it's the same values, right? It's 10 times 6 plus 5 times -3, 60 minus 15. We have 45 units of momentum, and that's the amount of momentum we had in all 3 collisions, whether they stick, they don't stick and waste energy as thermal, or they don't stick and conserve all their kinetic energy regardless. The initial momentum is 45 kilogram meters per second. So the final momentum also has to be 45 kilogram meters per second. So you have a mass of 10 kilograms moving with a final velocity v1 plus a mass of 5 kilograms moving with a final velocity v2. There are an infinite number of ways, mathematically, that you can satisfy an equation of this form. For example, v1 could come out to 0 and v2 come out to 9. That would do it. v1 could be equal to 4.5 and v2 could be equal to 0. There's no limit to the number of answers. v2, how about this? What if v2 is 1 meter per second? Then v1 would have to be 4 meters per second. Okay, but there's only one way in which you can satisfy this equation and then also satisfy this condition, that 1/2 m1u1 squared plus 1/2 m2u2 squared is equal to 1/2 m1v1 squared plus 1/2 m2v2 squared. There it is. We could have 2 equations for 2 unknowns, but this is going to be a fairly challenging bit of algebra or arithmetic. So what we need to do is combine these 2 ideas together, the conservation of momentum combined with the conservation of kinetic energy, to develop one combined equation that expresses those 2. So that's the content of the next video. Stay tuned, and we'll derive a special equation that applies only to elastic collision.